Hello. So I'm at home, and obviously we use a lot of electricity at home, okay, or anywhere else. And one of the things that everyone has is an electrical panel, and we have circuit breakers. Used to be fuses, but now we have circuit breakers over here. So what's going on? Okay. So what we're doing with this? Well, we all rely on electricity, but sometimes, for various reasons, we may end up with spikes, right? Sometimes we have spikes in amount of electricity, or sometimes a wire gets loose and we say there's a short circuit. As a result, we have this to protect all of the electrical systems so that we don't get hurt from there being too much current, right? So over here we have circuit breakers. In this video, what we're going to do is to look at what the purpose of circuit breakers and their older cousin fuses are, and look at some of the factors associated with circuits, particularly parallel circuits, that are important for us to consider in our safe use of electricity.
Hello. So the first one we're looking at is the idea of a short circuit. So let's think about this. So over here, you have a battery connected to a bulb. So normally, here's my battery connected to my bulb. Okay. The bulb has a certain resistance. So what's going on here is due to some wiring error. Okay, some wire now essentially allows you to bypass the bulb. So this has a very low resistance path that bypasses the bulb. Now that does a number of things. Number one, your bulb doesn't work. Okay, that's the most obvious thing. Because, well, let's look at it. The voltage across the very low resistance path and the very high resistance path of the bulb are the same. But now, because think about the current. The current's going to go mostly through the low resistance path. So the current, so with a short circuit, you get a very high current, okay, going through because the overall resistance of the circuit is very low. What you've basically got is a parallel circuit, right? That actually has because of this now in a parallel circuit, your overall resistance is lower than each of its constituents. Now it's essentially no resistance. Because of that, there's a lot of current going through, okay, and does a number of things. One of which is the idea that, think about it, your current is actually what is dangerous to you and what makes electric shocks dangerous. A high current, therefore, would firstly make it a lot easier for you to get shocked when you touch it. Number two is it can spark fires. Okay. The second idea is this. So here we've got a surge protector, and okay, so I want to plug in, say, my computer, then my printer, and then my monitor needs to be plugged into, I don't know, I need to plug in my TV, a few other things, okay? Obviously my desk lamp too. I want to plug all these things in. So guess what? I want to buy one of these nice extension cords, plug them all in. Oh, I don't have enough. I'm going to buy one more of these blocks too. Plug, 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 plug. Eventually, so what's going on? From a circuit's perspective then, so I've got a power supply. Okay, so first I've got, say, device number one over here. That's fine. But what you're actually doing is creating more circuits in parallel. Number two, device number three. And eventually you're actually lowering the resistance so much. Okay. Because the voltage across here is still the same. Across each device is the same. Eventually you're going to overload the circuit. And this again leads to a very high current, just like you would in a short circuit. and that's dangerous. You'll get fires out of overloading circuits as well. So it is important when you use those surge protectors and extension cords that you do not plug too many things into it and don't overload particular circuits. As I've alluded to before, the big danger to life is actually not the voltage per se, okay? The biggest danger is actually current. High voltage doesn't mean much if you have a very low current. And as current increases, the current going through you increases, okay? The amount of it becomes more and more dangerous to you, and at 0.07 amperes, it's probably how you would get electrocuted to death. So if you think about the dangers, one of the things we looked at, of course, was how short circuits might lead to electric shock. The problem with an electric shock, of course, is somehow you are conducting through too much current. And so we're going to take it from that angle and see how we might explain some phenomena and also some parts to maintaining safety based on this. So first things first, we're talking about grounding, right? So, okay, let me see, what plugs do I have? Okay, so quite often we have three-prong plugs over here. So as you know, I have a power supply here. These are the wires that actually go through to the power. So why do I have a third plug or third wheel over here? This is for grounding. So this is a plug. This wire actually connects to the casing of whatever device you have, okay, particularly if it's a conducting casing, and it goes into a wire that's deep into the ground. The idea is this: if you have a short circuit that involves the casing particularly, then what's going to happen is that you're obviously, if you touch the casing, then you're going to get a pretty nasty electric shock, because say if there's a wire that's gone loose, okay, let's think about this. I've got my casing here. So I've got a loose wire from one end, and this goes in to the device, does whatever the device does. This is so far not the biggest concern, right? Until you touch the case. Now, this is a low resistance path between you and the ground, and then somehow getting back. What's going to happen? You become the conductor, current goes through you, or if I do it, me, and you get an electric shock. The other grounding then is that this goes straight to ground. So instead of going through you, and you have a pretty high resistance overall, it goes through the ground wire and into the ground. Okay? And so in the event of a short circuit, it basically bypasses you. This works similarly, in fact, to a lightning rod. So when you get a spark and you're outside and it goes through you, you get electrocuted by lightning. The higher you are, the more likely you will be the path of least resistance for lightning. So the idea then is to create a path of least resistance for lightning. You don't conduct particularly well. I don't conduct particularly well. So, but you put a conducting wire up there. That's your lightning rod, conducting lightning rod. So this has a much lower resistance to go to ground than you. So instead of the lightning striking you, the lightning strikes the lightning rod. Yeah, there's current coming down, but it's not going through you, so it's safer. What about birds? Birds are known to. Another interesting one is birds. So you got a bird. So this is a high voltage cable, okay? High voltage power line. Now let's think about it. But what's the resistance in the wire? The wire's resistance should be fairly low. The bird, high resistance. So because the bird has a very high resistance, it has a very low current, and therefore it is perfectly safe for birds to just stand on the power lines. Remember how we say we don't want to touch plugs when we have just come out of a shower, say, or just finished washing our hands and don't dry ourselves off yet? Why is that? Well, most of the water we have a lot of ions in it, so they conduct electricity better than dry skin. You don't conduct particularly well. Your skin doesn't conduct particularly well, but the ions in water definitely will conduct. And as a result, when you do that, when you touch it, and you have wet hands and you touch it, because your resistance is a lot lower, you are prone to electrocuting yourself because your resistance is lowered dramatically. Okay, so that's why we don't do it. Now, one thing that people actually had to do back in the days of an electric chair is actually put conducting sponges on people so that when they get electrocuted, the current actually goes into the body, right? So it's a pretty delicate art back then. You have to make sure the current gets into the body and at a high enough current that the person would actually get electrocuted.